Hi everyone, and welcome to today's session. Today we'll be talking about a very interesting recent happening whereby the large language models, when combined together in a system, actually managed to win gold at one of the most prestigious math competitions called the International Math Olympiad, or IMO. This is quite significant because in the math benchmarks that we have so far, like for example, the math benchmark, GSM8K, as well as the AIME benchmark, all these have already been beaten like almost to 100% by large language models. But the IMO, the best language model based system, could only get about silver. Okay, it's not very easy. I myself have taken part in Math Olympiad before, not the international one, okay, not that good, but like the Asia Pacific Math Olympiad. And the questions are really difficult. Like they give you 1.5 hours for each question, but actually you might not be able to solve a single one. You might think it's a very long time. It is difficult because it is not an obvious leap from the problem to the solution. Sometimes the problem might be number theory, but in the end it uses geometry to prove it. It's quite fascinating and quite a good practice at using creativity and innovation to try to solve problems. So if the large language model is able to do things like this, it means that large language models might be able to combine and create new elegant solutions or new ways to view the problems by just piecing together pieces of knowledge that they have gotten from previous kind of questions or previous kind of experience, like in the training data. So all along, I've already known that large language models are quite creative. Like you give it a poem, you ask it to translate to Chinese or write it in Shakespeare style, write it in pirate style. No problem, the LM is able to do that, even though that may not actually have been in the training set. So mixing and matching things together is one of the key strengths of a large language model. And this is made possible, especially with like the self-attention mechanism, where you can pay attention to certain meanings of the words and using that to retrieve past memories from the weights of the neurons, you can actually do some form of creative writing. So, if math is a form of creative writing, why can't we use LLMs to solve math? And that's why we have today's session, all right? So why IMO? Or what is the IMO? IMO is one of the hardest math competitions around the world, and it's very difficult. It has problems in algebra, geometry, number theory, combinatorics, and many more. But one key thing about this Math Olympiad is that the questions are not meant to be like those kind of testing your calculation. Like they want to ask you to add 10-digit numbers with 10-digit numbers or multiply 10-digit numbers by 10-digit numbers. It's not the kind of like rigorous calculation that a calculator does. It's more of finding that unknown leap to bring you from one step to another step to reach the end solution. So most of the solutions here are actually quite understandable once you have seen them, but it's very hard to take that leap. Okay, so this is as I said earlier, it's about 1.5 hours per question. So 4.5 hour sessions over 2 days to solve 6 questions. All right. And each question is graded out of 7 points. 7 if you can, solve it fully with the right explanations and so on. Maybe you get 1 point if you just state a trivial fact without any proof, or you prove that trivial fact. There are different ways of grading. And why do we do this? Okay, because as I said earlier, the math benchmarks are already saturated. And these IMO problems, if you can solve it, it's something like multi-step reasoning, abstraction, innovation. All this came from the paper that the two researchers earlier. Let me go back to that slide. These were mentioned by these two researchers. I really quite like what they wrote in the paper because I agree with like almost everything in that paper. All right. So if we are able to do stuff like this can actually generalize beyond math. We might be able to use it for general problem solving. Right. So it's quite interesting to see whether large language models can do such tasks. So just last week, OpenAI claimed that they have gotten gold in IMO, and they released a set of proofs. And the proofs, while technically correct, it's very hard to read. Okay, it's not exactly the human kind of proofs. Then Google released shortly after, and this is actually verified by IMO as well. So they earn a total of 35 out of 42 points, which means 5 full solves because one solve is 7 points, right? So this is a gold medal score, and this is this is a breakthrough to me because it means that the large language model is able to reach human level creativity and robustness in terms of coming up with a math proof. And you see, the graders not only found their proofs correct, they found them to be clear, precise, and easy to follow, which means it's human-like in nature. And that's great because if we want an AI system to do stuff for us, it is best if they can talk to us in a clear manner. And this is an example of it. So this is from the IMO president itself, Dr. Gregor Dolina. This is from the Google DeepMind blog. You can check it out from the link below. So what does this mean, all right? In the past, the approach that we used to do math is that we will have to do in the form of domain-specific language, okay, a domain-specific language to prove the math theorems. Like, for example, if you want to prove this one here, like, for example, for every n plus k is smaller than n plus k, you can write this lemma over here or theorem over here, and you can use a language called Lean to try to prove it. So in Lean, you break down your proof into two steps. One is like induction step. So this is for your first sub goal, the n plus 0 smaller equals to n plus 0. Then you do some form of a successive iteration. This is like you just add 1. So like n plus k smaller equals n plus k is, you can infer that if you add 1 to both sides, it's still the same. All right. So these two combined together, you can prove the main theorem. Okay, this is the kind of way that we like solve this. So this is the proof of this statement. N smaller equals to m leads to n plus k smaller equals n plus k. So yeah, this is the theorem. And yeah, this is the starting fact. And this is the n induction result. And yeah, they start with the induction step, where the starting point is 0, and then you just keep adding 1, and then because this keeps holding, so this works. So you're able to do stuff like this in Lean. Okay, I'm not exactly sure how they do it computationally below, but you can write it out in program language, and this can be programmatically verified to prove that this lemma or this theorem is true. So this is Lean, okay, and this has been the dominant approach to do like most of formal math proofs for at least 10 years. Okay. So this came from the Hypertree proof search paper. I also covered this before by Meta AI Research. So this paper uses the Lean language and then uses some form of evaluation of each node. So they try to solve partial parts of the theorem. And then for each partial part, they go, let me just draw. They go down the tree. So like, for example, this is your starting part. You go down here. So you try to solve the theorems iteratively until you reach an empty set. So if you reach an empty set, it means you have solved fully already. So like what you have here, the sets here, like maybe we call it x, y. These are like stuff that you haven't solved yet. So for example, if you solve for x, you only have y left. Yeah, so this is a way of doing some form of iterative problem solving. You solve one part of the problem, and then you solve another part until you solve everything fully. Okay, so this is Hypertree proof search. The details a little more complicated, but the idea is like this. You go through, you expand out the various possibilities of solving. You solve each sub-problem at one time until you solve the full problem. All right, so all this can be done with this kind of domain-specific language like Lean, because we are able to construct the sub-problems in a programmatic way. We are able to construct the main big problem in a programmatic way as well. So this was what, before LLMs were dominant, this was the approach used. And with LLMs, we can also use LLM plus Lean, because we can use the LLM to sort of guide what kind of operations to use in Lean. You know, it's like something like tool use, you use the tool to go to the next state. Okay, and that's something like Hypertree Proof Search. They use, wouldn't call it an LLM, but they use a neural network to try to, see what set of tools or what set of operations should I use next. So this was something that I found quite promising, because I always believe in neurosymbolic methods. Like the LLM itself is not very robust. It's not very able to follow rules. Like if you ask it to calculate like 100 plus 101, okay, maybe you can, now this one is possible. Like you ask it to do 9999999 plus 9999567. Sometimes it will fail, because like the tokenization is not meant to be a calculator. It's meant to have semantic meaning of those tokens. Okay, but increasingly nowadays, the LLMs can do such things, and I suspect it's because the training set has become harder and harder in terms of math wise, and it's able to learn from those training sets. So if you give it training sets of 10-digit numbers, plus another 10-digit numbers, it might learn how to do that, just by having that in the training set. So LMs are not the best for robustness, but if you put in the training set, maybe it can still work, okay, with enough examples. So before like LMs are dominant, we use this kind of domain-specific language. After LMs became dominant, there's a hybrid approach. But what's interesting about this IMO solve by Google is that they didn't use lean at all. All right, I was surprised. Like, to be honest, I'm quite surprised because like we have spent the last few years trying to do stuff like alpha proof, alpha geometry that uses a very, very domain-specific language to try to solve stuff, like very grounded in some form of rigorous computational proof. But for IMO 2025 this year, there was nothing of this sort used at all. It's just the LLM itself, pure LLM with deep thinking. And if if I'm not wrong, there's no tools at all. It's just purely LLM, right? Of course, Google didn't release whether they use tools or not, but if there's tools, maybe that will be like Python programming or some computer programming tools. But with the paper that I shared earlier, with the two researchers, they are able to replicate Google DeepMind's result without any tools. So I repeat again, the IMO 2025 gold was obtained without using any tools, just using the LLM itself as the solution generator, as the verifier, is able, and also as the iterative improver, because they iteratively improve on the errors generated. They are able to solve the question. So that's a new paradigm. That's something that I didn't expect. Okay, because I always thought math you needed some formal grounding. Apparently not. Apparently the LM can judge itself. So I'm not sure whether this is because the IMO problems might not need that much robustness because it's tend to be simpler. You don't need a calculator to solve them. Or it could be the fact that LMs are just better now at doing computation. So which one of it, I'm not sure, but I'm just surprised that you don't need any formal grounding. You know what I mean? Like all along, we have been doing research, we as in general researchers, we have been doing research to do formal mathematics, to do it grounded in some form of programming language, in some form of mathematical rigor. You can see that the best performance was done in 2024 was a silver medal performance. Still quite impressive actually, but it required 2 to 3 days of compute. That's well above the 4.5 hours for 3 questions limit. And it needed a very, very strong set of domain language. But in this year's one, there was no need to have such a long compute. You can get goal performance within the limit itself. So you could theoretically run your AI within the competition time frame, and it can solve the problems within that time frame, just like human contestants. And it uses natural language. Okay, of course, within the 4.5 hours computation limit, there's a caveat here. We don't know how many instances of this LLM models are used. Okay, because in the human brain, there's only one human, right? But if you have like 1,000 LLM instances, that's like 1,000 humans. Okay, or you can argue that the 1,000 LLM instances might be the same as the human brain because we can do some form of parallel processing. So, I mean, it's very hard to compare computers versus humans. I think there's no real need to. Like, computers solve computer stuff, humans solve human stuff. But the fact that it can solve within the actual time frame itself is amazing. And this is probably the worst that it will become. I wouldn't be surprised if in the future it can solve it in 5 minutes. Because computers are able to do exponential speed up when the hardware accelerates and the software improves. It will soon surpass the human brain. I'm quite sure of it. And the key thing here is that it does this entirely in natural language. So there's no math language used at all. I mean, the language is in the natural tokenization of the English corpus, which also includes some math tokens. All right. So just using this natural language without a need for computer-specific language, like domain-specific language like Lean, you can get Go performance. So how did they do this? Okay, let's do some form of speculation based on the blog first before we cover what the researchers did in their paper. So in the blog, they did mention they use deep think, and deep think is something that is not really released yet. But what they put in the blog is that the deep thing considers multiple hypotheses before responding. Okay, what this means is that, a typical LLM, when you chat to it, you say that, you say add 1 plus 1. Then the LLM will respond, okay, 1 plus 1 equals to 2. Right? This is a typical LLM response. If let's say the user says like, add 1 plus 1, maybe with deep thing, what you will do is LLM version 1 might say 1 plus 1 equals 2. LLM version 2 might say that if I add 1 to another 1, I will get 2. Okay, maybe there's a third LLM that, okay, let me just write this somewhere so you can see it. Maybe there's a third LLM that says, 1 plus 1 equals to 3. Okay, this is incorrect. Okay, but that might happen because your tokenization, when you do the next token prediction, it's a stochastic prediction. There's a few probabilities for different tokens. You might actually predict the wrong token. Okay, if it's uncertain. If it's certain, it will normally be all the same token. So let's say we get all these three responses, we can pass it into a consolidated LM to say that, LM main maybe, you can just consolidate that 1 plus 1 equals to 2. Yeah, because you take majority, you consolidate and stuff. And sometimes, you get the wrong response, but overall, if you do multiple hypotheses or multiple parallel thoughts, the chance of you making an error is less. And people call this ensemble methods. So deep think might be a form of ensemble where you have the Gemini model itself give various responses, maybe with various kind of hints to guide the response in different ways, and have another LM to like consolidate what each of the LMs have gotten. So this is one possible implementation of deep think. I don't think we will know the specifics, but I've tested out something like this before. It works very well. It just costs a lot more. So I didn't really implement it in any of my frameworks I've created, but this is entirely possible. You can create something like that. You just ask the LM to respond in a succinct way, respond in a detailed way, respond in a creative way with some hints. You can get different responses, or you can just sample the LM K times. And then after that, from this samplings, you can, based on the above, based on this responses, come out with a consolidated answer. You can do that. So deep think might be doing that already. So generate n possible trajectories or k possible trajectories from the input prompt. You can also add in an evaluator step where you can say that, hey, is this answer correct? If it's incorrect, maybe we say no. Like you can have the LM do a verifier step, which again increases the robustness, because sometimes if your LM generates the wrong token by chance, when it evaluates itself, it can self-correct it. Okay. So you combine those answers that pass the self-verification back to the main one. So this is ensemble methods plus self-verification. So this might be how deep think works. And I think this is good for LLMs because LLMs being stochastic in nature. Okay, maybe I explain what's stochastic. Like for example, the cat sat on a, then you have to put in this token here. So sometimes the token is maybe mat is 70%, like this is the correct one. But sometimes the cat could sit on a, I don't know, on a rug. Okay, maybe not rug, maybe like on a paper. Yeah, so paper is maybe the wrong response, but sometimes you sample this, and then if you ask the LM to evaluate the cat sat on a paper, is this correct? Or if it's not, say what it should be. You can ask it to reflect like that. Yeah, of course, you could replace the cat sat on what, you can replace it with 1 plus 1 equals to what. So like 1 plus 1 equals to 2. Is this correct? If not, say what it should be. So if it's like 1 plus 1 equals to 2, then the answer could be correct. But if it's 1 plus 1 equals to 3, the answer is incorrect. It should be 1 plus 1 equals to 2. So LMs are actually quite good at catching errors that they probably already know in the model somewhere. Okay, if the model doesn't know of that, then too bad. It is a faulty self-correct because it might say that, hey, this answer is wrong when it actually should be correct. So in order for this self-correction to work, you kind of need the model to already know some form of answer in the main model itself. So like people have tried to do iterative improvements with the same LM, providing critique and then improving on the response based on the critique. It only works to a certain extent. And the main thing is that the LM needs to already have some form of understanding of this domain within its pre-trained weights, right? If not, it's just going to hallucinate the answer. Okay, so but if let's say the LM has already some understanding of it, doing this kind of step, multiple generation, evaluating them and combining the most promising answers, it helps to increase the robustness of the LM's response because we guard against the stochasticity of the output. Sometimes the output might be wrong, but we catch it again in a separate step because we look at the output itself and when we see whether the output works. So, there's this the reasoning models, they also work in a similar way, but theirs is a single thread of reasoning. So reasoning models are like that. If you have a reasoning model, you have like maybe 1 + 1 = 3, maybe. After that, this is step 1. Maybe it generates wrongly. Then step 2, it will say that, like, I think I made an error earlier. 1 + 1 = 2. Then, step 3, I'm confident of my answer. 1 + 1 = 2. So if we had let the LM just generate this without any form of like reasoning, like doing it into subtasks and then seeing the response and so on, it's not able to make a correction to its earlier response. Okay, this only can come about if we have a next substep or next subproblem or next subtask that we look at the previous output generated and we see whether it works. So if we are able to do it in a multi-step kind of manner, you can have self-correction inside the loop of the reasoning flow. So reasoning models are able to do some form of self-correction like that. But if you do it in a procedural way, like deep think, like speculative deep think, because we don't know the mechanism, but this is my speculation. You just do the generation, evaluation, and you combine the answers. You can effectively have a more rigid and robust way of doing reasoning. Because in reasoning, you don't actually control your steps. You see, all these are done by like an agent that just decides what tool to use or what task to do. So it can be a little volatile. But if you use some form of fixed procedural pipeline here, this is less volatile. This is fixed procedural pipeline. It's less volatile and helps to solve the kind of variance issue of the output generated by the LM. So I quite like this approach, assuming this is the right understanding that Google DeepMind has. But this is the kind of understanding that I would have coded in as well if I wanted a more robust system. So let's hold that thought for a while because we're going to look at how the two researchers do their kind of system and we see whether they use something like this. All right. But before I move on, any comments, questions, or anything you want to talk about, like based on whatever we've seen earlier? Okay, all good. All right, let's move on. So this is the thing that Google DeepMind blog tried to hint at what they did. So they use parallel thinking. So it's similar to what I mentioned earlier, generate multiple trajectories. All right, and then you see simultaneously explore and combine multiple possible solutions rather than pursuing a single linear chain of thought. So exactly as what I described earlier. So this also has the benefit of, not just being stuck in one possible solution. Because sometimes if your earlier context is only for solution 1, it's very hard to go to solution 2. By having many parallel branches, you can sort of get unstuck from local optima because you just explore more. It's like, having multiple humans do research. One human might do LM, one human might do knowledge graphs, another human might do, kind of vector databases with RAG, so basically this is diversifying. Like if you just have one person just doing large language models, you end up everything large language models. And that may not be the best solution for a particular problem. So by doing some form of parallel thinking, possibly with some form of hints to guide it to diversify its answers, you might be able to get better answers, right? So that's something that's cool. Like you can look at previous papers like AlphaCode. I think this was OpenAI. I think Alpha, Alpha is always Google. DeepMind. AlphaCode is DeepMind. So what they did is they have the ELO rating of the code itself, and they also have the language, which is like C or Python. So by varying the ELO rating and varying because ELO rating is like how difficult the problem is. So a less difficult problem, probably the output length will be shorter. A harder problem, the output length is longer. And like C and Python have different ways of doing problems. Some problems like big numbers, you use Python, you solve it instantly because Python has an inbuilt big number computation. Some problems, if you want more efficiency, you use C. So by varying the hints over here, this is the hints in the sort of metadata. By varying this and then generating the code after that, you can sort of give very diverse kind of generations that are able to, maybe one of them might work. So AlphaCode works like this. They generate multiple solutions. They see whether one of them works by verifying them on the training set, on the like sample test example. Okay, because for this kind of coding competitions, they will normally give 1 or 2 test cases for you to try out, see if your code works. So they can verify the code on the test case, keep only code that works. All right, so you are able to have a very, very efficient way of like multiple generation of all codes and just selecting only those that work with a verified solution, because you know what's the input and what's the output for that test case, and you keep only those that work for it. You can do a similar approach for the UP AGI challenge. You basically can do multiple generations of solutions like Python code or whatever code you want to use, or you can even generate the solution directly in terms of a grid. And then you see whether that grid or that program managed to generate stuff that works for keep only those solutions that work for the input output, for the sample input output. So you are able to do that because you have some example to test on. All right. So this is something that parallel thinking can unlock. And it's not new. It's just that we haven't really done it in a very predefined or well-defined workflow. And I think like this deep thing makes it in a well-defined workflow. But it's not difficult to implement. It's really not difficult. Right? So the other thing that they said they did is that they enhanced the reasoning capabilities by training it on more multi-step reasoning, problem solving, and theorem proving data. So that could explain why the base model of Gemini 2.5 Pro seems to understand the theorems much better. Okay, because if you give a large language model without such training, you give it math theorems, it's going to not understand it. All right, it's going to think that it's not a theorem, it's just some chunks of words, like writing a poem, that kind of thing. And I try to match my poem, which is not robust enough. You need to understand the math proofs. And the good thing about LLMs is that LLMs learn the training data really well. So a lot of the improvements we see with LLMs right now is because our training data has become a little more multi-step in nature, a little more problem solving in nature as compared to those stuff in the wild. We give it a lot more benchmarks that evaluate it on critical thinking, and the LLMs are able to capture some essence of it. So the LLM improvements right now, while architecture plays a role, the training data I think plays an even larger role. Those with access to high quality data will have high quality LMs, right? You can see this in the Phi 3 model, like textbooks is all you need, where like you just train it on high quality Python textbooks, it can output code quite well, even for a small language model. So the training data is really very important. And so this is one way they make Gemini better. And look at that, a curated corpus of high quality solutions. So it's not like starting from scratch. It knows past responses to past IMOs. And so this IMO is not out of the training distribution. It's actually within training distribution. Just that the problem might be something that it has not encountered before, but it might be able to make some match. And also they have in general hints. Okay, so hints can help to guide the model to think in a certain way. So all these are useful. to guide the model to respond in a way that is appropriate for your use case. So yeah, this is what DeepMind did, and I think nothing out of the norm here. All of these are totally within the bounds of expectations that we have for large language model. It's just that the way that it's executed is so clean and simple. Like no longer do you need to convert something into a rigorous mathematical language. You can just use normal English language to just write the problem in English and then ask it to output the solution. And that's really cool. Like that is really one way of making AI accessible for all. You can just talk to it in normal language and it can respond to you in that way that you need to. Just one thing. Okay, I'm not sure whether you have seen it. This alpha code and the ARC-AGI challenge has something that IMO doesn't have. Can you see what is the thing that it doesn't have? Or what makes IMO harder than all this? Why is IMO difficult? Are you able to verify your answer? Okay, so the answer is, yeah, do you want to give it a shot? Do you think the IMO generated answer, is it potentially verifiable with some training set?
Yeah, so IMO is mathematical proofing basically. And if it already has a previously curated data set of high quality solutions, the mix and matching will be a lot simpler, and the verification step of the pipeline is a lot simpler with things like ArcAGI and or possibly AlphaCode, but mainly ArcAGI. ArcAGI is a lot more difficult for verification because the problems are unique every time, and the pattern matching is a lot more difficult and requires much more general reasoning algorithms.
Yeah, I mean, in that sense, maybe the diversity of our AGI is higher than IMO. But in terms of like having something to verify whether it works, like IMO itself, I don't think it has any like training, like test cases for you to try out. Like it's essentially either the proof or no proof. Like there's no like, hey, if your proof works, it should work on this. Like, you get what I mean? Like if I want you to prove, like proof that all angles of triangle add up to 180 degrees in a 2D plane. Okay, it must be specific. Okay, because non-Euclidean planes, the angles. Yeah, you want to do something like that. There's no real. I mean, in my opinion, there's no real intermediate way to test it. Like the proof either works for all cases or it doesn't. Or it can. Okay, maybe you can create your own test cases. So yeah, it's possible to create your own test cases because you can test out. Case one. Case one is like that. It's case one, isosceles triangle. Case two is maybe line. Case two is a line. And maybe case three is a equilateral triangle. And then case four maybe is any triangle. So maybe it's possible to test out like partial solves of the proof. But the problem itself likely doesn't give you like step one, step two, step three, step four. Yeah, if you get where I'm coming from.
Yeah, I do. It's not so much more, it is multi-step, but it's more so it's very, I don't want to say abstract, but the reasoning process and proofing has to all be done internally. So you can't really, how would I say it? It's not feedback because our gauge eye is different. The feedback is different anyway. You still have to do the proper pattern matching, but with the proofing, it's a lot more internalized. So you don't have anything for your use case. And when you go about the proof, you have to kind of roll out the proof in real time. You have to reason it out step by step and kind of like have that confidence already in the proof by the way
Right. Actually,
you
the proof will involve breaking it down into sub
the
cases. One case,
yeah
yeah, that's
the
part of the proof as well.
yeah.
Yeah. So I mean, in terms of like my understanding, I think it's actually harder to do math proofs than it is to solve like a programming problem or an AGI challenge because you don't really have the feedback that says that, hey, are you in the right direction or not? Like, there's no test case you can use to solve, unless you can invent your own test case. You're like, okay, does it work for this sample case itself? But you need to think of these cases yourself. This is not given to you. Isosceles, equilateral, all this, especially if you're talking about a domain that people don't have names for it, you might just call it two similar angles, three similar angles. You might give your own name, but it's very hard to say that, hey, make sure that it works for this case because the cases are not given to you in the problem. So in order to solve an IMO problem, you kind of need to know how to do your own breakdown of the problem itself, and you need to know how to solve step by step. And sometimes one step leads to another step and another step. You need to have that sequential chain of reasoning in order to do a proof.
Right, right.
Yeah.
So that's why you're calling the LLM pipeline very creative, because the whole thing is internal of the LLM and it's internally natural language. So as to internally process all of these rollouts and all of these hypotheticals at the same time, and also roll them out, and indulge the line of thought and see where it leads to. If the proof is logical and not a non sequitur, the logic has to be logical. The logic has to follow itself and be able to be back traceable via the or during the sub goal and sub decomposition of the problem into subtasks and sub goals. While you're doing the proof, you have to break it down, and while you're doing your rollouts at the same time of the proofing, you also have to roll out the proofs in parallel and have the confidence to navigate them all at the same time and know which proofs are logical and have a sequitur to them, and which ones are non sequitur and don't have a logical conclusion to them. If that makes sense when you're doing proofs, because
Yes.
I've done proofs in high school and stuff. I've done like the college class, what do you call it? The college proofs where you do your practice tests. I've done a couple. I wasn't good at them. But I've done a couple where you have to write out your own, like you said, chain of thought. You have to write out your reasoning, and then you have to put the equations that follow logically with your reasoning. They have to match. Otherwise, it's kind of gibberish and you're kind of rambling.
Yes. Yeah. So I think that's the difficulty of IMO. Like as mentioned, as what we discussed, like you need to do your own reasoning, you need to know how to do pattern matching, and you need to like keep your earlier reasoning traces intact to solve the next few. And actually, that is why I think maybe approaches like Lean in the past might have failed because Lean is very highly structured. It's harder for me to tell you something in a programmatic language than it is in English. Because like in English, there's about a lot of nuances and I can talk about the same thing multiple times. But if I want to do it in programming is a very rigid, very clear-cut, concise language. You don't repeat yourself. Yeah, that is a little unnatural to how we think actually. And by making all proofs in a programmatic language like Lean, we sort of constrain ourselves in terms of like how we think. Yeah, because the programming language may not be as robust and may not be as versatile. Like I faced this issue when I was coding for the ARC AGI challenge back then, like last 2 years ago. I basically used a Python program to map the input to output. And I realized that for stuff like, for example, you have a square here, right? And this square inside is a hole, right? And what we need to do is we need to fill maybe this hole with all holes with a different color. Like for example, if within this square, I need to fill it with a red color thing. So I need to color it red. For us, visually, it's very easy to see because we have the idea of objects and the idea of space in an object in a kind of visual sense. But if you ask a program to do this, it's very difficult because you need to like do some form of boundary finding, and then after that, some form of flood view within that. And that really is not easy to express in a programmatic way. But in English, you can express it as fill in the holes of all the squares with red color. Yeah, that's one sentence, and that in flood field language, maybe it's about 5 to 6 lines. So it's very difficult to express a concept that does not exist naturally in programs with programmatic language. And that could be one reason why for IMO proofs, the Go level performance was done with just the LM itself without any programming tools. Maybe because the way we express math proofs is something like a language. It makes a lot more sense to just use language directly than to use a symbolic method. Okay, so I've been thinking about this, like why didn't we use Lean to solve it? Because I all along thought using Lean might be correct, but this result really changed my understanding of it. Like I start to see that maybe using programs might be restrictive. Like even for the stuff that I did for our AGI challenge, I have a feeling that once we have a very robust visual output pipeline, visual input to visual output, like right now, even with visual language models, the input itself does not really capture the position that well. But once we have a input output pipeline that captures position quite well, we can solve the AGI challenge with just the visual pipeline. All right, we don't need the program. So that's what I think it would gravitate towards, because this challenge is essentially mainly a visual that all that stuff. Those not very visual, but those humans cannot really solve anyway. Yeah, so so I do think that the right domain that you use to solve the problem matters. And here the AGI, the domain is vision, right? But all along we've been trying to use programs to solve it. So maybe that's the wrong approach. AlphaCode, the domain is code, so that's why we can do coding quite well. In fact, coding is one of the things that LLMs can do very well, right? Code is sort of like a language that you can sort of learn. Okay? But in terms of like expressing the code out, we also don't express the ideas out by computer program. In fact, when we do reasoning for code, like LM generates code, they actually first do does some reasoning, like say, oh, the user asked for this feature, I need to do this feature, the best way is to do this. Then after the LM explains to itself one chunk, then it proceeds to code out the code. So that is I think a great way, because it uses a high level kind of planner and then after that executes it out in a low level code. If you were to just output the code directly, the chance of error is much higher, because code is not natural. Like I don't talk to you, like um, print hello world. This is not natural for me to say like that. Or like for I equals 0, I smaller than 10, I plus plus, then print I. That kind of stuff is not natural to human language at all. In fact, it is a struggle to understand, because it's very like very mathematical in nature, very like it's not even the IMO kind of math. It's more like it's a kind of math that you need to really understand how the computer works. Then you can appreciate that for loop. Yeah, it takes a while, because I thought people programming before it's not a natural concept to come up with. Okay, but for IMO kind of thing, the way that you write the proofs can be natural, because like you can explain to them, hey, like for example, if I want to talk about the for loop, I can say I start with I equals to 0, and then I increment I by 1. I keep doing so until I is 10, or I is 9, because I is more than 10, right? So you can write this out in natural language, and that could be a proof. Of course, the proof would be induction, for you start with the base case, and then you prove the induction step I plus 1 smaller than j plus 1 or something. You could do something like that. Um, and actually all this easier to do in English than in Lean. Let me explain to you why again. Look at this Lean proof for this statement. N smaller equals to m is leads to n plus k smaller equals to m plus k. So in normal language, you could say that start with base case, n smaller equals to m. Then you say next is we do the induction step, where n plus k smaller equals to m plus k equals to n plus k plus 1 small equals to m plus k plus 1. This is a direct proof, by the way, because you just add 1 to both sides. It preserves the inequality. Then you have your conclusion. Hence, n plus k smaller equals to m plus k for all k in real numbers, or for k in integers in Z. Yeah. So basically that is the kind of thing that you would do for English. And you can see that, what do you think is easier to read? Like is this an easier proof to read, or is this an easier proof to read? Anyone? Which one do you think is easier to understand? The math-based proof in computer programming language, or the English math proof here, that you just use English and then interface with some math symbols here? Anyone? I just want to get to know your thoughts. Like, do you think it's easier to understand like proof number 1, which is in Lean program proof, or proof number 2, which is in English language?
Yeah, I see what you mean. So it's the readability. But also I think with the LLM, with English and its expressiveness, the chain of thought is more natural. So like when you are breaking down your steps, the steps follow each other a lot more naturally. Um, well, if you're trying to output it all in the domain language purely, and then trying to run that, and I think the LLM, I think it depends on the training data too. I think how good the LLM is with the domain language matters a lot with its training data. But from a general standpoint, I think getting an LLM to kind of grasp language and then use that to build math reasoning almost, I think is a lot more natural, instead of just feeding it just, pure domain language and then having it work it out by itself in order to try and create something coherent. I think it's a
Mm,
lot more difficult. I think English or language in general is a lot more natural in and of itself. It follows itself more naturally. So you can have more complex reasoning in English. So, and it's a lot easier to lay out that reasoning than in a domain language where you're trying to write out everything, in a very pure symbolic way.
definitely. Yeah. So I think that's one reason why LMs alone without any tools work for IMO, because IMO problems itself caters for a bit more fluid kind of expression, right? And that you don't really get if you were to use a domain-specific language, right? Next up, just want to talk a little about
Sorry,
alpha
sorry,
evolve.
sorry, sorry.
Yeah,
I
sorry,
want to
yes.
push back a little here. So I think the main point you shared here is the reason that LLM is space reasoner is it's better at solving math problems because it's more intuitive and the natural language more expressive, right?
Yes.
And humanly understandable. So my first point is um human understandable have better human understandability does not really translate to machine being easy to understand. So because like this
Yes,
is like
yes,
we
yes.
understand because we are used to language, but for LLM because it's trained on human data, that's why it can understand and its output is also easier for us to understand. But it does not necessarily mean for other type of AI system, for example, Lin, um, its own output is I can't even understand. It's always challenging for it to understand its own output. I don't think that's necessarily the case. So um yeah, so basically we are just viewed from a very uh or I don't know super anthropomorphized way. Like yeah. Another thing is um in terms of expressiveness, I do agree for math proof is very important. But even if you um for more formal math proof, right? I think it's the structure itself already limit a lot in terms of how expressive it can be. It's not exactly like the the way we usually speak or write in natural language, right? So
Yes, definitely. Math is more restricted.
because we really, I think, doesn't matter how you brainstorm. At the brainstorm phase, you can do a lot of things whatever you want. But at the end of the day, when you write down the actual proof, it has to be very rigorous. And that, by itself limits the expressiveness because it has to be rigorous, even though you are writing in a mix of math symbols and English or whatever language. Because you want it to be rigorous, by definition or by nature, like it cannot be too expressive. So that's the two things I want to push back. Exactly because of that, even though the proof in link here is hard for us, it's not very intuitive to understand, and it might be very rigorous. But for someone like who already get very used to this programming language, and for that person who is both well versed in this language and in math proof, maybe for that kind of person, he might feel this too. Actually, in terms of expressiveness, maybe it's about the same. This is my hypothesis because I'm not familiar with this programming language myself. So
Yeah, I agree with you that math itself is a restricted form of English language or natural language. But I would also like to say that you also would agree that the lean kind of proof is even more restrictive than the math language, right?
can you give one example? Sorry, I missed the first part.
Yeah, no, you would agree that this proof here is more restrictive than if I were to do it in English, like I do
I
it.
would say it's inefficient for sure, because you also mentioned like something you can write in English, you need so many lines, right? But it's inefficient for sure. But if for every mathematical statement you can write in English and plus math, you can find the corresponding form in this language, then that means they can express the same thing, right?
Yeah, because actually in this language itself, you don't really have your reasoning parts here because your reasoning is all in math. But sometimes your reasoning is like, suppose this is m is a prime number, then it only has two factors. So something like this, if you were to write things like this and you want to express it in lean, it might not be okay. I guess you can express it somewhat, but you might be able to express more things in English language. Like hence, in order to have a divisor, we need to consider these cases. So sometimes when you write stuff in English, you are able to do some form of thinking. And I don't really, because I've done like programming a lot. In programming, you don't actually do the thinking in that programming language. You
Yeah,
actually think
I
of
do
what,
agree.
yeah, you think of what you want to write first, and then you translate your thoughts into that programming language.
Okay, so I think the hypothesis here is what's critical to solve this type of problem is not necessarily the formal proof you write down, but it's the brainstorming part that's more critical, because that kind of bias you towards certain space to search, right?
That's right.
Yeah. So, but that bias by itself does not need to be very rigorous, because you just want to have a rough idea of rough technical approach you want to work with. So for that stage, you do not need to be too rigorous. And for that I do agree. Program it's very inconceivable to do that with a programming language, because yeah, it's just very inconceivable.
I mean, why do you think the like ChatGPT or Claude Code outputs so many commands in the Python code, right? One reason is it helps with reasoning. It helps with thinking like, oh, okay, this is for doing that. This code is for doing, like it is for looping through all the variables and checking whether any of them is greater than 10. Yeah. So some stuff like this, if you put in your commands, it helps you do your reasoning steps. But the reasoning steps itself, they are not explicitly mentioned in the programming language. The programming language just strips down everything into just the pure hard executor lines.
Yeah, and also wonder, because I also, again, I missed the first part. I wonder how they use this kind of mass proof language, right? How they even do the initialization part? How do they even start to which search space are they going to start with? Because it's very hard to imagine they can find a effective way to start their search. Whereas for language based, they can use the internal reasoning or the thought part. You can pick and choose oh, I might need to start with this approach, then they just, just continue.
Yeah, yeah.
But it's programming language is, yeah, I have no idea how they're gonna, how they,
Like,
how they did that part.
exactly. So in programming language, it's harder to put your chain of thought inside there. So one thing is if you use natural language, it's easier to put your chain of thought in there because you can write anything. I mean, like not anything, but you can write more things than what the more constrained programming language can do. And some more the training language itself, the training data itself, it's more common to have people writing math proofs in natural language than it is in Lean. Right? Lean requires a separate um, hand engineered step to translate the proof into Lean. Someone needs to do it. Maybe LLMs can do it with enough training data, but there's more English or natural language math proof out there as compared to programmatic math proofs. I mean, based on my understanding, of course, I might be wrong, but if you talk about most data that you can see online, giving it asking it to generate a solution more in tune to the training data, which is like the natural language based proofs, might be easier than it is to generate a lean based proof. Yeah. Okay, so I will continue because in the interest of time, I'll just move on. So I want to highlight some similarity with the approach that is in DeepThink and AlphaEvolve. So one thing is that in AlphaEvolve, this was again by DeepMind. So this basically says that I have some past good example of programs. I select some to act as context, and then I ask the LLM to output, some potential edits to the programs to make it better. So out of these programs, you can evaluate, and then you can give, some selection. So give from this evaluation, you can put them in the database, and then you can select those high scoring ones again to sample again to generate more prompts. For more details, you can check my video on this. But the idea here is that in order to do self-improvement, you need some form of a nice evaluator here so that you know which kind of solutions to choose to improve. So it is possible to use some form of evolutionary based method to improve the solutions for IMO. This kind of requires still some human in the loop knowledge because for IMO problems we don't have a ground truth evaluator. Like it's hard to say that this solution is correct. Unless you have a DSL to prove that it's right. But if you were to use a DSL that proves that it's right, you will keep getting it wrong, 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 wrong until you get the right answer, right? Because math is hard to get the right approach from start to end. It's very, very hard. It's easier to get it somewhere midway. Then you need some creative step to go to the next part and so on. So if you were to use an evaluator that is like based on the DSL, you may get a 0 score for your evaluation because like you don't get answer. Or maybe you can talk about how many steps you have in the evaluation, how many steps you have in the proof. But again, if you have how many steps but you don't reach the goal, then that metric is again quite vague. You kind of need something to tell you, how close you are to the goal. People have come up with many ways to verify, like using the LLM to see how close it is. But even LLMs itself are not that great at judging how close a solution is. All right. So how does one know the answer without the ground truth? If we were to use AlphaEvolve, maybe it could be a pair programming thing. The human looks at the potential solution, like solution 1, solution 2, solution 3, and the human says, hey, I think solution 1 is better. Go by that approach. So like a pair programming, like what you do for GitHub Copilot, or like basically any Copilot, like, you tell the LM what is the approach to take. And the LM comes back with suggestions. Then you choose what you want. Choose what suggestions to incorporate. Let me just put this here. So something like this, you are able to use the human as a way to do the evaluation, to say that, hey, what should be done, what should not be done. Okay, but for IMO, unless you have a human, to be there to guide the solution generation, which is possible for harder problems. Like you can tell the LM, oh, using number theory is a better bet than using geometry because you know that the problem is something in number theory. Okay. But again, human intuition might be wrong also. We might think it's number theory, but in the end, it comes out with geometry. The LM might be right. Yeah, so it's very hard to have an evaluator for a partial proof. Very, very hard because you don't know which one is closer to the goal. Like sometimes the proof might be totally out of tangent, but that solves the problem. Like if you look at like there's this thing called knot theory. So knot theory was the guy who invented the game of life, John. He's also a John, but I can't remember his name. But yeah, basically he has an open proof that only was solved like just like 4 or 5 years ago, and the proof had nothing to do with knot theory. He's using some visual proof. So it's like sometimes the proof is totally in a different domain from what is the original domain itself. And that's why there's open problems. Because if it's in that domain itself, people might mix and match and solve it. But LLMs actually might be better at doing mix and matching than humans, okay? Because we have only a limited fraction of the available knowledge. LLMs know a lot more. So, no, human in the loop might sound great to help the LLM improve here, but it might actually hinder the performance. So, if we don't have a human in the loop here, how? Then we have the question, can the LLM judge itself? All right, and with that in mind, let's move on to the solution that was provided by the two researchers. How did Gemini 2.5 Pro get the goal solution from IMO 2025? And essentially is just LM, multiple sampling, there's some filtering, okay? Because you use the verifier to filter. Okay, verifier will generate the errors and then you correct the errors iteratively. Just on first glance, it sounds like I'm doing a coding problem. Because when I do vibe coding, I generate the code, I feed back the errors back into the LM itself. The LM comes out with the solution, I try again and so on. But the difference with vibe coding is that this verifier here, for code, the verifier is your compiler, whether it compiles or not. Or your verifier can be yourself, where you see whether the UI is correct, functionality is working. So there is a verifier. But for math problems, how do you verify? Like you can have the human verify, as what I mentioned for AlphaEvolve loop, the evaluator, you can be a human. But again, as I said, the human might be not incorrect, because sometimes you have a more biased way of viewing things. You miss out what could be done in a larger picture. So how can the LLM verify itself? And that's exactly what we are going to find out now. Can the LLM verify itself? This, if any, is the key takeaway of today's session. Can LLM, yep. Sorry, yes.
Yeah, I just want to clarify. I don't really understand what does it mean by IMO does not have ground truth.
Oh, because it's asking you for a proof. So there's no like test case you can test out. Oh, if you put 2 in, the output should be 5. It's like competitive programming questions. They normally will come with some sample test case you can use to verify the input-output relation. But for the IMO proof, there's not really an input-output relation. It's just, can you prove the statement?
But if you are careful enough, you can check your proof whether it's correct or not, right? That's verifiable.
Yes, but you can verify whether your proof works, but sometimes you might miss out edge cases. Sometimes your proof only works for a certain subset of the original question, that original statement, but you don't know because you didn't consider those cases, like edge cases, or like the proof might use something that is incorrect assumption.
So when you say it's no ground truth, that comparing with
Programming languages, yes.
Yes.
Programming competitions, and also like the AGI challenge. There's a ground truth that you can use to compare to, like the input-output samples. But for IMO, you don't have such things.
I'm not sure about it. Sorry, why ARC challenge has
Or Arc AGI challenge, they also give you some sample input-output grids. They might say that, oh, this is a square here for the sample input, and then the square goes to the right over here. So you have this is the input to the output. You have some examples of input-output relations. So you can test it out.
But for your test set, it's totally private, right?
Yes, it's different, but you have some examples to, at least the program, it should be able to solve the test cases. And then this is the training sample. Of course, with this training sample, you may not be able to solve the test, but at least your program is on the right track if you can solve the training samples. You get what I mean? Like the verifier is to check whether it works for known examples.
Also, I think I remember, if I recall, the last question in the IMO is not a proof question.
Oh, it's a compute question, is it?
It might be a combinatorial type of problem. I can't remember exactly, but it's not asking you to prove something.
Correct. But even for those kind of questions, how do you know your answer is correct? It's an open-ended answer.
But okay, but my initial question was like, when you say there's no ground truth, what I was thinking is I was comparing with research type of question, because for research there's really no ground truth because you are proposing something new. But for IMO, being as hard as it is, it is I mean, it came out by some professionals, and they do have the ground truth. So I was thinking along that line. So when you say there's no ground truth,
Oh, the person who set the problem might have the ground truth because he sort of knows the answer.
they have. It's not. They definitely have.
Actually, the problem setter might also get the solution wrongly. Sometimes they might miss out certain cases. Yeah. So what I'm saying, you don't have a ground truth is even if you have the solution, the proof itself, it might not be correct. Like because you might miss out certain things, your assumptions might be wrong, some inductive step is wrong. It's hard to verify.
So for the IMO, don't they judge the quality of the answer based on how correct it is and how much you cover with your proof, how objective and logical it is?
Yes.
Like the quality of the proof is it's about the quality of the proof, right? It's not a yes, no. It's
Yes. So
the
it's a score from 0 to 7.
right. They judge the objectivity and the quality of your work and how much it covers.
Yeah.
So
In
the
fact,
ground
sometimes your solution might be totally different from the base solution and you still get full marks. Because if you have shown that you can solve it in a different way and all your steps are sound, you can get that one question right. And that's what happened for me. Like I did Asia Pacific Math Olympiad. I used a totally different approach, but I still got one question right. So
precisely,
yeah.
yeah.
So you are saying there is possible there is no unique solution. That's what I see.
Yeah. I mean, for math proofs, there's many ways to do it.
Okay.
I asked you to prove 1 + 1 equals to 2. There's more than one way to do it. You can use number theory, you can use geometry, you can use a number line. You can use many things. Yeah. There's many ways to prove one statement.
All right.
Yeah. So that's the difficulty. There's no hard verifier. You see, like there's no way to verify something for sure. Like even the best proof might have a gap. And the person who created the proof might not know it until someone points it out. All right. So let's see how this works. All right. So this is the key insight for today. One is that how do we verify the LM? How do we verify the answer? That's one. Second is LMs itself may not be good enough. But if you use LMs in an iterative process, in a pipeline, it might be much better. So this is the meme here. Apes alone weak, apes together strong. You replace this with LMs alone weak, LMs together strong. I guess this summarizes the approach that we have today. It's really just LMs all the way. Like no joke, there's no two U's at all. It's just LMs after LMs after LMs, prompted in different ways, in different parts of the pipeline, and it works. So, all right, let's unveil the magic and see how it works. Okay, so this is from my previous video of how to do like how many instructions can an LM follow. Like we should try to avoid this kind of prompts, like do step 1, step 2, step 3, do constraint 1, constraint 2. Try to break down the problem into sub steps. Maybe you can do your constraint check separately. This is a much more robust pipeline. So one LM might fail. A pipeline of LMs, lower chance of failure. Okay, because you break down the problem into simpler, manageable steps that an LM capability can handle. And by iteratively improving on the solution, you basically take away a lot of the stress that one LM needs to generate the answer. Okay. In fact, for research, it's also iterative improvements. Why should we force an LM to get it right in one step? We should do it in multiple pipelines. And basically, that's the whole idea of the solution. Let's take a look. Okay, this is how it's done. First, you use an LM to generate the solution. In fact, more than one solution. And then we ask the LM, okay, based on the solution you have, check yourself whether that solution makes sense, whether you need to add more steps, any of the steps needed to improve the robustness of the solution. Okay, after that, you use an LM to say, okay, you are now a judge. All right, now you see whether your solution works. I'll see whether this solution provided to you works or not. So, this part here is the student, maybe student generates potential answers. So it's a separate prompt. So after you get your answers, the teacher judges the answers. After that, you have the student critiques teacher's suggestions, because the teacher may not get it right. Sometimes your verifier might give you wrong stuff, like you submit a review for NeurIPS and back comes, hey, who is Adam? Why do you because the paper put like, we trained this model using Adam, with the Adam with optimized by Adam. And then the reviewer wrote back, who is Adam? Then you could criticize, no, Adam is not a person, Adam is a method. All right. So sometimes the verifier might be wrong, but the student should critique, student incorporates feedback to improve the solution. So it's like the peer review process. It's imperfect. But through this imperfectness, you allow both ways communication, the judge as well as the submitter, eventually it helps to improve the solution. And then you go back to the judge again, you go back to the reviewers, like the reviewer say, hey, not good, not good. You need to add more experiments. Okay, I'll do it. Okay, blah, 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 and put back. No, not good enough. Yeah, by the way, paper review process is similar. Okay, you need to get your paper rejected a few times. They're like, but I don't feel like doing this anymore. But no choice. I have to do it. So continue, continue improving until finally, the judge or the teachers finally says, I think it's good enough. I think it's good. Okay, reviewer 1, accept. Reviewer 2, accept. Reviewer 3, accept. Reviewer 4, accept. Reviewer 5, accept. Okay, meta reviewer says, I accept. All right, so essentially the workflow is a peer review process, right? But of course, if let's say someone says, hey, this idea is not novel. Okay, reject, done. All right. So there are ways to improve the solution. The idea is you give multiple potential answers, you ask it to verify, you keep improving iteratively, and then after that you go through a process to accept. In fact, this acceptance process is not like say you must pass. I mean, you not say you need to keep iteratively improving. The solution can come in straight away, and if the verifier says it's great, okay, again, we don't just accept it straight away after one round of being great, because sometimes the verifier makes mistakes. You run through the verifier 5 consecutive times, and this 5 times it must accept continuously. So it's like a bit of robustness check. And you don't actually change your verifier. It's just that the LLM itself is stochastic. So sometimes the output is accept, sometimes it's not. And I know this accept and reject is not just output accept or reject. You also need output reasoning. So sometimes this might this might affect the final token that's generated. Right? So this is what is done. Questions, anyone, before I go into like some details? Okay. Yep, Derek, yes.
Yep. Sorry. Yeah. So the pipeline. So it starts with the multiple sampling. And it just starts with that sampling. It doesn't sample again after that. It just goes through refinement until it consecutively passes and it gets its final solution.
Correct. So there are
Okay.
2 parts of this pipeline here. The first part, actually, they call it the agent. Every single agent is just one solution. So like you start with one solution here. This is like maybe solution 1, and solution 1 will go through this whole pipeline with only the idea that this is solution 1. So it's like you improve solution 1, becomes solution 1A, then maybe it goes to solution 1B and 1C and so on. You keep improving solution 1. There's no solution 2, 3, 4, 5, 6. It's just solution 1 all the way. Okay, so it's one agent, but they run this pipeline across multiple agents. So like you could have solution 2A, 2B as a separate agent as well. Yep. So eventually what you will do is you will just accept those solutions that pass through this whole verifier process.
Gotcha. So it's parallel iteration. It's
Parallel
parallel
iteration.
refinement.
Right. But the
Okay.
verification, you don't put more than one solution inside. You only verify one solution at a time.
Gotcha.
Yeah. In fact, I think this might be an improvement to AlphaEvolve, because AlphaEvolve, you pick like 3 possible or 5 possible solutions, and you put them together, ask the LLM to consolidate the solutions together. Sometimes being diverse hurts the performance, because like if you have 5 solutions that are totally different, how do you consolidate them into one? So here, when I say multiple sampling, is actually sampling across agents. All right, you can look at their code. They have a parallel agents version. So a great thing about this is it's all open source. So kudos to the researchers. I love open source work. Keep it up. Keep up the open source stuff. We will make open source great. All right. So I'm also doing open source stuff. I like the open source community. Yeah, my projects like Agent Joe and Strict JSON, fully open source. All right. So over here, multiple sampling is multiple agents actually that are doing this whole process. Imagine multiple students, like maybe 1,000 students submitting a paper for peer review. Some papers are accepted, some papers are not. Eventually, we take a look at all the accepted papers and maybe we pick one for the answer. That's how the pipeline works. Clear? All good?
So if this is a multi-agent approach and all of them are in parallel, so how does it break down the problem?
Oh, all these are done using prompts.
No, but what do you mean? So this whole process will be iterated multiple times?
Yes, this whole process, if you look at the arrows, this is how the process can go. So like the first LM generates something, second LM improves it, third LM critiques it, fourth LM, this actually is together, critiques the critic and also corrects based on the critic.
So each
Yeah.
step is handled by, so it's like both parallel and sequential have
It
different.
is sequential for this pipeline, but parallel as in you can run this pipeline in parallel across multiple agents. So this is one agent. So maybe I cancel out the multiple sampling here. One agent just sample it one time only. Yeah, it's just that because we have multiple agents, that's why we have multiple samplings of the solution.
Okay, so but when there's multiple agent going through the same pipeline, at which step do you synthesize all the
You don't. The agents don't interact with one another.
not even at the end? Then you have multiple solutions, then how?
And you maybe have a pipeline to pick them up. Pick one of the solutions.
Which is not shown here.
Yeah.
Okay.
So I mean, of course, you might say that yes, like for AlphaEvolve, in between the process, I might have like you have a database of solutions, and then you pick one based on heuristic score, or you pick K based on heuristic score to prompt the next solution generate. Yeah, you could do something this like AlphaEvolve. Okay, the good pros and cons. Pros is that you can have diversity to mix and match the solutions. Cons is that you might confuse the LM. So here, for IMO, I think they didn't use this method in the end. I don't even know whether they tried this method, but it's also because the token length reached its limit. Like if you were to look at their step one later, I will show you the slide. The thinking tokens itself is not sufficient to generate even one solution, right? They have to do that step twice. That's why there's a step one and step two. Step one, they think for like, I think they use 32768 tokens for reasoning. And then they had to use another 32768 tokens here because the first set wasn't enough to generate a good solution. So if you were to combine multiple solutions into one prompt, I think the bottleneck is the LM reasoning tokens. Yeah. So potentially, if the reasoning tokens are increased, you could potentially use an AlphaEvolve method to perhaps synthesize good solutions. I do think there's a benefit to synthesize solutions. So that's what is missing in this workflow. But just by doing one solution and iteratively improving it and just accepting the right solution, it works quite well already. I mean, like, I'm amazed. I'm amazed that it can even solve the IMO question just like using this pipeline. No tools, just LM calls.
Sorry, what do you mean by you don't know whether they actually use this pipeline or not?
No, they use this pipeline. As in, I don't know whether they tried out something like AlphaEvolve. Because AlphaEvolve is something different. You actually use multiple solutions, and based on the top K solutions, you form your context, and then you use that to prompt the next generation of the next cycle.
Okay.
Yeah. So I think AlphaEvolve might be superior, but in terms of token length wise, I think not enough for solving IMO questions. All right.
Okay.
So step one, initial solution generation. So this is from their paper. Run the model some number of times, obtain some initial solution samples to the problem. All right. So this one, actually, if you look at the code itself, essentially they only run it one time. All right. But some number of times is when you do parallel agents. But in the code itself, they only run to get one solution sample. And then after that, they basically hope that one of the agents have some overlap with the correct approach. Okay, and they might give some hints to guide. Like question 1, they ask to use induction. Question 2, use analytic geometry. I don't think these hints are cheating because there's only so many domains that math has. You could easily have one agent for each domain. That's perfectly fine. And these hints don't reveal anything else other than the domain that you need to use or the step that you need to use. Let's say there's 10,000 possible steps in math. No problem, you just have 10,000 agents. I think it's not cheating at all. It's fine. Yeah, it's just maybe compute-wise might exceed the human brain, but we are not comparing humans to computers in terms of compute size anymore. We're just seeing whether the computer can solve it. So I think this is totally fine. This should be encouraged actually, because using hints help to diversify the answer. Just like AlphaCode, they use the ELO and the language to diversify the code generated. Using hints help to diversify the proofs. I think it's fine. The prompt itself emphasizes rigor than finding the final answer. And this is very important because it's very hard. It's very, very hard to get the proof right in one step. Okay, so it's more likely that you will get a partial proof and then you iteratively refine and get a better proof. So LMs likely cannot gauge accurately whether the answer is correct anyway. So you don't emphasize, hey, answer must be correct. You emphasize rigorousness of the steps taken, make sure that each step is provable, and that LMs can do because it's a narrow one. Like for example, like prove that the induction step works. You could do that as an isolated case, and this is also what is done in hypertree proof search. They make sure that it's rigorous for that particular subproblem, and they keep solving problems that are not part of that subproblem. Okay, because they already said, okay, this subproblem is solved, let's move to the next one. So this essentially helps to solve the problem in a multi-step way. Don't need to get everything right, but whatever you have must be right. Okay, because if whatever you have is wrong, then it doesn't matter how you do the next few steps, right? You are still going to be wrong because if you base your assumption on a proof or a lemma that you have previously thought you have solved, but that lemma or proof is wrong, then your whole proof is wrong. All right, so it's very important to get the parts of the proof right. And that's why I think the prompt emphasizes rigor. This is very important. Don't ask the LLM to do stuff it cannot do. Like to ask the LLM to say that, you must find the final answers is like, asking you to invent quantum mechanics when you have no idea what's a quantum field and everything. You have no idea about the experiments, ask you to invent it. Like it's hard. But if I give you like, hey, find out how to do superposition and so on. So it's like I guide you step by step. What's the quantum wave function, step by step, and eventually prove quantum mechanics. Then you can do it because you have the steps already. So I like this approach. In fact, we should do this approach when we do like problem solving. Don't focus on getting the full path to the answer. There's an initial direction there. Let me just draw a diagram here. It's quite important. Like for example, this is the start state, and this is the goal. There's no need to go to the goal directly. You could just, like make sure that you explore in multiple different directions. And then eventually one of those explorations, you might take another step from here and then, oh, I reached the goal. Oh, that's good. And the thing is, because LMs can do goal-directed exploration, because you can put the problem in the context and the problem contains the goal already, which is the proof you want to solve. You can essentially do a multi-step exploration at each step. And each step itself will try to guide you closer to the goal. Of course, some steps cannot. So that's why you need multi-agent. If you just use a single agent, some agents might fail, but some agents succeed. Some agents would succeed at finding goal while others fail. Okay, so multi-agent reasoning is important because if you just stick to one agent reasoning, if the agent fail, it's gone for you. But if you have hundreds or thousands or in the future, billions, zillions, quadrillions, I don't know how many zeros you want to add based on your compute power. In the future, when you have a huge number of agents, it's okay if some of them fail because some will succeed. And that's what's important. Some will succeed, right? Step 2. Okay, it's a little late. I hope you all can have another 15 minutes for me. I will just cover the rest of the slides in 15 minutes. All right, step 2, self-improvement. Okay, Self-improvement is basically, as what I said, the tokens are 32768, not enough to get the answer, right? So they ask the LM, okay, here's the previous reasoning, reason even more, right? So you could continue the generation, right? That's also why, AlphaEvolve like methods, I think, will have difficulty here because you put 3 different approaches, like you just have only one approach right now. It has problems thinking already, like problems doing the reasoning, the chain of thought. If you put 3 different solutions at the context, you probably can't reason very well, right? And it might lead to model collapse, so the model might just give up, right? So important to do what the LM can manage, and I think they did that here. Next, ask the verifier, which is an LM, to generate a bug report. Okay, so notice here the verifier. Notice the verifier is not a pass-fail, Okay, it's important here because if you do a pass-fail, you might not get enough guidance. It's like reinforcement learning, right? Reinforcement learning, you only have the reward, and the reward is a sparse signal. It's not good for learning. What is good for learning is if you have constructive criticism. So if you are a teacher, do take note, okay, you just give an exam score, it's not that great for learning, Like if you just tell the student, you need to work on this domains, that might be better than just giving a score like, oh, you are good, you are bad. Yeah, that rarely works. All right, constructive criticism is the way we learn. And this is exactly what this bug report does. We generate a list of issues and they classify it as either critical errors or justification gaps. And for each issue, you also need to explain why is that an issue so that we don't just take your word for it. We actually can understand your thought process. So this is, again, why LLMs in natural language is superior to domain-specific language like Lean, is that you can add reasoning traces easily. Like you can give an explanation in plain English. If you were to use a computer programming language, it's a bit hard to write this chain of thought stuff inside a language, right? So this bug report will serve as useful information for model to improve the solution, fix errors or fill gaps. I like this approach, right? So next, bug review. You actually can verify the verifier. You can say, hey, this issue is not an issue. This issue is a mistake, right? So if let's say there's a mistake, this issue will be deleted from the bug report, right? So there's a to and fro here. It's not like the verifier has the final answer. You can also challenge the verifier. And then after that, you can correct the solution based on the bug report, right? And then you repeat again these steps of verifier, challenge the verifier, correction, repeat a few times, and you only accept if it reliably passes the verifier. So, as I said, actually this step 3 is not different for a complete solution and the starting solution. It's actually the same step. So after this verification step, after all the bug reports, there's also an accept and reject token outputted. Okay, if I remember correctly. So you can actually base your accept reject based on, like, when you get a list of issues, you also know whether accept or reject, right? And most of the time, if you have a list of issues, means reject, right? I mean, because bug report means it's not correct. So if there's no bug report, likely is accepted, right? So you keep doing this until you accept it. And they do this, I saw a for loop of 30 times. So they do this whole step from step 1 to step 5. They do this 30 times. So they do the iterative step 30 times, see whether it generates a correct solution 5 times in a row. If it fails to generate, then we mark that whole process as failure. So of course you can increase the iteration to 100 times, 1,000 times, but I think for IMO, probably 30 times is enough because that's what they use in their final code. So this is a key takeaway that I had, is that the verifier is not perfect. And that's also okay because the system still works. So this is from their paper, right? Our system is quite robust to errors made by the verifier. We iteratively use the verifier a sufficiently number of, okay, their English is not that great, but they iteratively use the verifier sufficient number of times. So it's about 30 based on the code that I saw. If it misses the error in one iteration, it can still catch it in the next iteration. So again, LLMs are fallible, but if you iterate it many times, the chance of it failing a lot of times is less. The token stochasticity, you just need to output it multiple times, you reduce the chance of it, failing all the time. You might catch an error because you repeat the same prompt 5-10 times. Maybe in one of these 5-10 times, you will catch it. So that's why they make sure that the verifier must pass 5 times in a row, okay, to guard against stochasticity of the tokens. Okay. Again, if it claims that an error is not an error, okay, this false negative may not go through the bug report step, okay, because you can actually take out the bug, right? And then, you see over here, if let's say the model does not agree with one item, is encouraged to revise its solution again. So basically, the solution might still be the same, but it's revised so that as to fit with the verifier's understanding of the solution. So sometimes the verifier says, oh, you miss out a constraint. The student might think, actually, this constraint is not that great. But it doesn't affect the proof anyway. Let me just add in that constraint. So, it's basically iteratively improving its solution such that the LM as the critic is satisfied and the LM as the student is also satisfied with the critic. Right? So it's like a two-way process. It's quite cool actually. It's like a real-life interactive agent dynamic. One student, one critic, one student, one verifier, and you just keep talking to one another until you come to a consensus. And that's such a beautiful thing. Yeah. Just using LMs alone, you can come up with a consensus, and that consensus works for IMO to get the gold medal. See, ultimately the presentation is improved. So this has a lot of analogs to how I do like coding, vibe coding and stuff. I'm one agent. The LM is another agent. We keep talking to one another until we are satisfied with the solution, which is the code provided. So why not agent talk to another agent? Sometimes it might lead to collapse because the agent might not agree with one another. But most often times for more advanced models, it's able to play the role quite well, and it's able to come to a nice consensus. So this is one thing I want to. If you take away something today, just take away this. You don't need a perfect verifier. You just need a system to do iterative correction. And that's the key highlight for today. You don't need a perfect verifier. Okay, all along I've been thinking that yes, your verifier must be robust, must be math-based, must be grounded in mathematical language like Lean. I actually bought into the Lean idea quite readily. But I do think now that perhaps a soft verifier, which means that it may not be coding based, it may not be a hard kind of yes/no verifier. It might just be a verifier that is based on LM judge maybe. But if you use it enough times in a sufficiently robust system that does some iterations, it might be possible. Of course, the LM as a verifier, the LM needs to know some things about math. It cannot know nothing, right? Because if you ask someone to evaluate something outside of their domain knowledge, it would not be great. But here, the Gemini 2.5 Pro is trained with math proofs, so it knows stuff about it. So this is my concluding thoughts. Using LM as a verifier is not a good idea for robust proofs. Okay, it can give the wrong answer. But it worked in this case because Gemini already has a lot of math problems in their training data. And it kind of fits the format that it has seen before. So if you want to use the LM as a judge, make sure the LM has the training data needed to be the judge, right? And the LM need not be a perfect judge, but it shouldn't be too shabby. Okay, it should still be quite good. Okay, not perfect, maybe it's like 90% accurate. Yeah, you don't use a judge that is 10% accurate. Okay, that's not gonna be very good for the system, right? So it means that in the future we might be doing judge with an LM if we have sufficient training data and we have sufficient reasoning traces that can enable such a judge to work. So like what you saw earlier in the blog post by Gemini, they actually train the Gemini 2.5 Pro model on multi-step reasoning that is based on the IMO problems and high quality solution data sets. All these are very important for using LLM as a judge. Okay, don't be misled by this paper thinking that you can use the LLM for everything. This domain is well explored by Gemini. DeepMind has been trying to solve this problem for years. So this is a well explored domain. You don't just use an LLM as a judge for any domain, all right? And the next takeaway I have is that it might be better to convert, okay, this is not really a takeaway. This is more like for increased robustness. I think there's one step that might be helpful here is that instead of just using the LLM to verify directly, because it's a soft verifier, it's not an objective one, maybe because it's the chain of thought reasoning, that the reasoning traces that are important to generate the next few proofs, and all this can be done in text-based reasoning. But to have more robust proof of whether, or robust checks whether this proof works, why not convert this text-based reasoning into the DSL, like Lean, and then use the Lean to verify? Earlier I said, Lean is not great with expressing reasoning traces, but no problem. We already have the reasoning traces expressed already. We have this whole long text proof. Why not convert this text proof into a DSL and use the DSL to verify? That's an objective check. Okay. The only thing is, unless the math proof itself is unable to be expressed in Lean. Okay. And I think this is quite likely because some proofs are very, very hard to express in a math language. All right. I have to seek some expert guidance on this. I don't use Lean much. So mathematicians, if you are listening to this in the video feed next time, let me know whether Lean can express all your math proofs easily. All right. So that will be the answer we need. I suspect it's not easy. That's why this step may have been omitted. All right, because even in the Google Gemini IMO solutions, I don't think they converted it to Lean. All right, but it should be quite a straightforward conversion, right? A text proof convert to Lean. I'm sure LMs can do that. You can convert human language into a code. Lean is a code. I'm sure you can do that. Why didn't we do this? All right, why didn't we do this?
Wait,
It
wait.
might be, yeah.
Yeah, so on this point, right? Link can only verify if you have gone through first.
No. Lean can verify your proof. So like your proof itself, you can write into like mathematical equations in the computer form, and then you can run the Lean program.
Oh,
Lean
yes,
will
I
help you
see.
check. Yeah.
Okay, I see.
Yeah, so I'm thinking, why not have a mix of both worlds? Why not be symbolic as well? Use Lean for the proof checking.
But isn't that what they have been
They have
attempting?
been using Lean as the way to generate the solution. But
As
I'm saying that
I was referring to, I don't know, like, is it alpha proof or alpha geometry? I
I
think
think alpha geometry, uh, I do think they use Lean as well. Yes. But
I'm pretty sure they use hybrid approach. One of them, I cannot remember. But
Lean
the fact
geometry
is,
should be alpha geometry.
but the fact is not they ditch all the. So basically, they now favor pure LM approach over the hybrid approach. Right?
Yeah, I'm
But
actually curious.
my point is, I think this has been tried before.
I'm curious why it failed.
Yeah, same.
I mean, no explanation was given to this, and I suspect Lean is not enough to express all the proofs. This is my suspicion. Yeah. So if we were to use a very constricted or constrained language to judge something that's a bit more expressive, then it doesn't work. So maybe Lean is not sufficient for the proofs. Back then I hosted Michael Hodel, who did DSL for AGI Challenge. So I could write his name here. So he's a very smart guy. Yep. DSL for AGI. And certain DSL could be 20 plus rules or relate lines of code. And that is something for stuff like, you have you have certain like blocks here, and then the rule is that every time you hit a block, you go to every time you hit the block, you something like this. So the rule could be something like every time you hit a block, you go to another direction. So this is the starting state, and the end state could be like you just fill up this one with yellow squares like that. A problem like this, for humans, just need two rules saying that if you touch a brake, you turn left. You touch the brake at the bottom, you turn left. You touch the brake on the right, you turn down. Something like this, two steps needed for human rules. Like human rules is like, I can't remember the exact problem, but it's something like that. If you touch a brake from the bottom, you hit right. If you touch a brake, okay, when you touch a brake while heading down, you hit right. If you touch a brake while heading right, you head down. So just two rules like that. Two lines of words in English. In the DSL itself, it's actually 20 lines of code because the DSL had no idea of what's heading down, what's heading right, because all these are very, very, very specific for this problem at hand. If you want to code out a DSL, imagine for induction, you need to code out the inductive step as one operation. Then maybe if you are doing something like solve by contradiction, you might need to code out that contradiction as another operator. Then maybe another proof solved by visualization. How do you code that out in DSL? Like that is visual. Some proofs by math are visual math proofs. Like for example, there's this visual math proof I'm going to show you now. This is proof that half plus 1/4 plus 1/8 plus 1/16 and so on, it adds up to 1. All right, you keep doing this, it adds up to 1. How is this done? Because you keep adding up a slice of this square, at eventually the final slice will be infinitely small, and hence you have the whole square, which is area 1. So this is how you prove 1/2 plus 1/4 plus 1/8 plus 1/16 plus, yeah, so the visual proof is this. How to write this in Lean? You tell me how to write this. So there are some proofs that I don't think Lean can express. And the same thing for the AGI DSL. You can't express certain things, especially when things are a bit more different from what you have seen before. You might need to come up with a new operator to write it. But the cool thing about English language is that if something is new, you might be able to come up with a way to express it with just words alone. Like for example, if you have a red car, right? You know red car maybe is maybe we just call a word. Maybe I don't want to give a brand, but maybe we call a red car Alpha. And then you have no name for this green car. But guess what? In the English language, you can just say green car. No problem. You can combine green and car together, and you don't have to say the word alpha, And it's very versatile in terms of what you can express. You can express a lot of things. Again, you can't express all things, but you can express most things. And it's much more expressive than using a computer language. So I suspect the reason why this is not done is that the DSL is not enough for everything. So Lean might be too restricted. Yeah. Derek, you wanted to say something, right? I saw you unmute yourself.
Yeah, so I was gonna ask, so would it be better to implement, is it faster to implement DSL or the DSL purely for low level executions and keep natural language at the high level reasoning? Or are researchers just trying to convert everything to just pure LLM pipelines? Is it just faster to make the LLM do everything, or is it faster to have the DSL be a separate tool call for low level execution and keep the abstract reasoning and creative problem solving at the high level and kind of create like two separate I don't want to say pipelines, but two separate modules?
Yeah, I think it's possible to use a DSL to verify stuff. But again, as what I mentioned, even you use a tool call for the DSL, you might still not be able to get the answer because the DSL might not be expressive enough to explain whatever that is in the text. Yeah. So
Okay, so
yeah, it's nothing
so
to do
there's
with tool calls. It's just about
yeah.
expressiveness.
So if everything is being expressed in language at the high level already, because that's the only way to get the most expression and most creative problem solving in mathematical proofing. Um, would the DSL even have a use anymore? Because I mean, in theory, you'd want to use a DSL for something that's low level and simple to verify, right? Not something that's complex to verify, but something that's very simple to verify. And it can be 100% objectively correct, right? Just so you're not wasting LLM calls over and over again, trying to iterate and land on the correct answer, if that makes sense. You can have a low level uh, proof or low level solution you need really quick and use a DSL for that while you keep everything else at the high level with natural language reasoning.
Yeah,
But I'm trying to
I
figure,
agree. agree. You can do that provided your DSL can express the stuff. So actually, I'm very keen to use a more robust method to verify the proof rather than using LLM. So I like the idea that you have everything in the text reasoning domain and you convert down to a verifier to just a low-level verifier to just see whether it works. I mean that should be the way, in my opinion. Like there's a more neural symbolic way, and it's a bit more robust than using LM to evaluate.
Right, but it sounds like researchers, what they're trying to do is they're trying to make the LLM do everything, and they're
Correct.
trying to make it one single LLM pipeline. So I'm trying to figure out if there's a reason for that. Is it just faster to make the LLM do it all at once and then do an iterative pipeline on it, and then you do away with the DSL because the LLM has such high quality data from the corpus that it can do all of the verification from scratch, and it has all the potential to get the final solution. You just need to bring out that potential from the training data via pipelines, via agents and stuff like that. The what do you call it? The test time scaling and all that. You bring out the potential from the data set. So it could be that the data is just so powerful and has so much to it that the LLM is kind of supercharged. And then once you go through with implementing the agentic pipeline, you can maximize that return on investment from your training data.
Mm. Yeah, I mean, I don't have an answer to that because I don't know the reason why we don't use the DSL. But I do think that if you have a DSL or you have basically a verifier that is objective in nature that can help you prune out certain pathways that are not correct, it will definitely help you in your exploration faster. You can explore more promising pathways by pruning out those that don't work. Yeah, so I think there's merit to this idea. Yeah, I hope that answers. I'm not sure whether that's in line with what you're asking.
No, what I'm saying is that DSL is my intuition as a low level tool call or as a low level verifier. But like again, like I said, there's a lot of research papers trying to make the LLM do everything and make it a single pipeline. So it could be they're trying to simplify the architecture. Maybe there's issues with the DSL, and maybe the LLM doesn't work with the DSL well. Maybe it's too much for it to handle. Maybe it's easier to make the LLM do everything internally and just make it into a simple pipeline. But again, like you said, we don't have answers to that.
My gut feel tells me there's an issue with the DSL.
Yeah.
Because DSL, unlike LM and mix and match of English language, DSL is quite fixed. So once you have a DSL, it doesn't learn actively while you solve new problems. In fact, humans need to put in the operators. Like if you look at the Python language, right? Like Python language might be great for expressing stuff, but that's because we have many modules, many packages added in by people that are maintained. And they are kept with the times. So you might think that, oh, I can write code and I use code very well, but those are maintained by people. The DSL is evolving if you are taking Python as a DSL. Like if you were to just use Python from 10 years ago, you likely can't solve a lot of things right now. You might need very long code just to do it. But for Python, it's short because it's all in the package that people have created. So if you want to use a DSL to prove it, your DSL needs to be continually updated such that it's very expressive. And it's easy to write in DSL. Yeah.
Okay. So maybe that's what they're missing. They need to have something where the LLM can adapt and improve the DSL in real time and update it for its whatever it's problem solving.
Correct. So one thing I like about coding benchmarks is that, when you have compiler, you have the compile errors. That is something that we are missing from this IMO side. So this could be, I mean, Lean could help to fill in this gap for simple proofs. You could ask Lean to prove the sub-steps, but the more creative leaps like the maybe visual proofs, all this, you don't use Lean. So you might be able to use a subset of the DSL to prove certain steps. I think those are okay. So that's one advantage coding has over math proof is that you can have more reliable errors because you can run this code to generate the runtime errors, and you can have the visual errors, which is like you can use a human or like visual LM or VLM to check whether output UI meets specifications. You could have that, so that could be another loop that you can use. So all these are verifier loops that is possible, but you can't really do that for math proofs because you don't know whether what you see is what you get, you see? Like, like math proofs is not a direct output, is correct means correct. You kind of need to have the steps correct. So it's a little different here.
I think another reason is, as I mentioned just now, Math Pro only is only one part of IMO, right? Not every question is IMO. Sorry,
Yeah, some questions are open-ended answers, right? Yeah. But even so, you also don't know whether your answer is correct.
I'm saying this lane-based hybrid approach cannot be used for that type of question.
Yes, you are right. You're right. Yeah. Okay. I would say you are right with a caveat, is that I don't know enough about lean to say whether that's possible, like open-ended questions. But I do think lean is for proofs, not so much to answer like short answer questions.
Not short answer, like combinatorial optimization. There's so many type of math questions, right?
Yes. So yeah, I think we answered the question. I don't think the DSL is enough. Yeah, simple fact. I don't think the DSL is enough. And if you operate only on the DSL level, you're operating at the low level. It's like, if you want to move from place to place, I can do a high level. I move from this room to my kitchen. Or I could say I move my left leg, right leg, left leg, right leg. It's harder to move left leg, right. In fact, if you go down to the muscle level, oh, this is a contractor muscle, extensor muscle, and I move my muscle level, you go down even further, you go to the atom levels, maybe you go to the action potential of your muscle cells. Like, it's very hard to control it at that level. It's the most precise. Okay, let me just draw this. It's a very, very important thing. So the higher you go, okay, the higher level planning you go, you have imprecise because it's very vague, but you write the least or express it. While at the bottom, you have the most precise, but you write the most. So you can talk about like cells, or you can write about like maybe Python language, and here's assembly code. Python is very not precise. You don't get to control where your memories are located. You don't get to, I mean, recent versions maybe you can, but you don't get to control where your memories are located. You don't get to control the runtime environment, the just-in-time running kind of thing. You don't have like a ways to break out of parallel threading. Not very easy. But if you want to control all this, you can. You can use C, you can use C++, but you need to write more code. So you want to go down even, you can go into assembly code. You can even go down to FPGA transistors and so on. So you get more and more precise as you go down the layers. But it's harder to plan here. But you can go to the most, write the least. Maybe Python is not write the least. Write the least is free text. Because you can just express everything, like say I want an app that helps me like send an SMS every time someone comments on my YouTube. No, just like this, free text. Then you go into Python code, maybe it's 100 lines. And then you go down to assembly code, 100,000 lines. Yeah, so that is you could express everything in a certain level. Maybe you could do error correction at this level. But it's very, very tricky because you need to, you want to do error correction at any level, you might need to know all the errors. You need to know all the modules or like the tools at that level. So it's hard to do that when your level of operation has many operations. Very, very hard. Yeah, so perhaps by doing it all at the free text level, your error correction is the simplest, right? Because you can just error correct just by writing new lines of text. Yeah, so there's some pros and cons here. It's not robust, definitely, but it is the easiest to correct. I'm not sure whether what I'm saying makes sense, but there's different hierarchies where you can do your error correction and iterative improvement. And for IMO problems, it seems like free text is the better way. All good?
All good.
Yeah. This is mind-blowing for me as well. I always thought that you had to use some programmatic approach to solve this. Apparently not. So, AGI, maybe don't use programs. Maybe just use free text. Yeah. We might even use such a pipeline to solve the ArcAGI challenge, and just use a VLM that for ArcAGI, use a VLM as input to get the stuff, and also use coordinate grids as inputs. Because you could give both the image and the grids. And then the output here, when the output comes out, output is in grid. Like, yeah, I know it's a bit weird why you put VLM as input but not VLM as output, because LMs or VLMs are not good enough with output positions yet. Right, so you can output as grid, but for ArcAGI, it's perfectly possible to use both visual and grid as input, and then do the reasoning in free language, and then output in grid. Yeah, I think that's perfectly possible, and you skip the program altogether. Yeah, so, and that's also possible only if you have good enough training data and multi-step reasoning traces that Gemini provided. So you look here, for those wanting to solve ArcAGI, ensure that you have this inside the LM training data. Okay, if not, I don't think this approach would work. Okay, very, very important to have this. Okay, oh, wow, it's so late already. I guess this was a very interesting discussion. Questions to ponder, right? Let's quick one. Can we self-evolve math solutions without the ground truth answer? Yes. Use LM as a verifier. Okay, so you don't need the ground truth. You just need to ask the LM to verify. And note that when they verify, they actually ask the LM to generate a list of issues. So these issues are grounded in critical error or like lack of justification. Okay, so it is basically a schema used. So you don't just ask the LM to output, not just output, pass, fail, or accept, reject. Output it in terms of a constructive feedback in a schema. Okay, guide the LM in a way to respond. And yeah, this is very important. It's not just I use LM prompting for everything. How to prompt it matters. And using a prompt that enables the LM to come up with something a bit more objective in nature, a bit more modular in nature, helps a lot with the critic process, right? And I think this is the key takeaway of this paper. Even an imprecise validator or verifier can work if we put in the right structure, right? Next, should we use pure text-based or domain-specific approaches? I would say for this case, why is it disappearing? Okay, pure text-based or neuro-symbolic approaches. I would say in this case, the text-based might be more expressive and easier for error correction. Okay, and that's also because like IMO, you don't need that much robustness in calculation. It's not meant to train your computation. It's more to train your idea generation. So a lot of times the solutions are very elegant and simple. Okay, so maybe that's why it works for IMO. If the paper is more of a calculation paper, then it's best to use the domain specific language for that. Right? So it might be because of the nature of IMO problems are more expressive and creative in nature. Okay, more expressive, creative than computative. Yeah, in fact, I've done like a lot of math Olympiads before. A lot of times they like to ask you questions like this. Let me give you an example. This is not math, this is not IMO, but it's like local math Olympiad standard. You might get some questions like this. What is, or ask you to evaluate 110 times 19 times, oh no, sorry, maybe evaluate this -5 times -4 times -3 times dot 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 times 1 times 2. Okay, maybe over here I will put a bit harder, right? Maybe put -504, so it makes it harder. Then over here will be like 496, 497. Anyone want to guess the answer for this? What's the solution of this sum? Oh, sorry, I made a mistake here. So this should be, let's just put it as 505. Okay, -505. Anyone want to guess what's the answer for this?
I feel like it's like a very elegant, simple solution, and then you have to write out the proof for it. I don't know. Does it cancel each other out somehow, or am I wrong?
Is it 0?
Yeah, answer is 0. You know why? Because if
Okay.
you do minus minus 1, there'll be like this part here, -1, 0, and 1. You will actually multiply a 0 in the middle. Yeah, so stuff like this is
Uh,
Math Olympiad questions that typically ask,
Wait,
I'm
for
not too,
real?
yeah, I'm not too interested in giving you like a calculation question that you need to have a billion digits as answers. Not oftentimes the questions are like that, more elegant in nature. And a lot of times you don't need to have a lot of compute. In fact, if you compute too much, you are probably on the wrong track. Math Olympiad questions need very little compute actually. Yeah, it's more of understanding than lots of calculation. Yeah, and if you are ever intending to take part in Math Olympiad, most of the time the answers are of this form: 0, 1, and like the year of the Math Olympiad. So like the year that I took my Math Olympiad, like the local one, Singapore one, I think it was 2002. So there are some questions that I didn't know the answer. I just put 2002. And I got a gold medal for that year because I sort of guessed the mentality of the exam setters correctly. Like, so yeah, it's always like that. The Math Olympiad questions are like that. They are meant to be elegant. Yeah.
Wait, so I think that in light of this, I think it makes much more sense why they ditched the symbolic approach, because I think symbolic approach is very good and robust for a calculation-based question, but if this is like more like brain twister or trick question.
Yeah, yeah, yeah. It's a lot of these kind of questions, Yeah. Yeah. That's why I say it's meant to test your creativity, not meant to test your calculation. Yeah, it's to see whether you can see that pattern or pattern within patterns. The more patterns, the better, like it's about pattern matching. And LMs are great at pattern matching. This is actually the perfect domain for LMs to be applied on. Yeah. So maybe you don't even need the program. Just need the way to pattern match. Right? Of course, with the right training data, you can do that, right? Without the training data, um, LMs can be quite bad at this kind of problems. Right? Next, would multiple imperfect verifiers that cover multiple domains be sufficient to solve a problem? Depends on the problem and the verifier. But in general, it's a good approach. Okay, because sometimes you don't have the verifier. Like sometimes if you want to do a program that helps you to like maybe find out the optimal way to arrange a schedule. Sometimes you don't have that optimal way without like sometimes the way to get the optimality is so hard. It's like it's exponential calculation. Like there's so many constraints. Everyone has their own constraints with their schedule. Like person A might tell you, oh, I don't want to work weekends. Person B might tell you, oh, Wednesdays I have lessons with my kid. I cannot make it. Person C might tell you, hey, yeah, whatever person B is on, I don't want to be the same schedule. So, it's like very hard to schedule everything like that with a rigid planner because every time you plan something, maybe person D comes in and says, hey, you know what? I don't want to do any day that person A, B, and C is doing. Or like person A might suddenly change. Oh, now weekends I'm free. I don't want to do Wednesdays anymore. You know, it's very hard to have a perfect way to plan everything. And if you have a multiple verifiers to just say, oh, is person A constraint met, person B constraint met, person C constraint met, person D constraint met, and you feedback them and ask the LM to plan again, that might work better than having a rule-based planner. But of course, if you can use rule-based, please use rule-based. It's 100% accurate. But if you cannot, LMs might be the next best thing. Like there's this thing called LM modulo. I have done a session on it before, like where you use multiple verifiers and they feedback the error messages to the LM to correct again. This works pretty well. So I would say that multiple imperfect verifiers that cover multiple domains might actually work better than just one verifier that is imperfect. Or in fact, it might even work better than having something that is perfect. Because something that's perfect is rigid. It can be very rigid, like a very rigid planner that you can't change. Okay, 1 minute or 2 minutes. Anything else to add before we end for today? Okay, if not, thanks so much for staying. I extended about an hour past the thing. You can look at the prompts here about how they generate this at your own time. So you can see like this is the verifier verdict, you see, final verdict, invalid or what. Then it also gives like either a procedure or justification gap. There's a schema that is needed. In fact, looking at how the prompts are generated is a very good insight as to how they came out of it, right? So look at this. I think this is quite nice to incorporate into our LLM pipelines because schemas are important. And so let me just conclude again by going back to the main slide here. Okay, I think LLMs alone may not be great for a lot of things because for a lot of like multi-step reasoning things, they are great for single-step stuff like translation or extract entities. These are great. But for multi-step reasoning, like you need to do step A, then do step B, then do step C, that builds up on the previous steps. You kind of may have difficulty just using one LM or even using LM with a single line of reasoning, like what most reasoning models are doing, because you might get into the wrong line of reasoning at the start and you just fail. So maybe do it in the form of multiple agents with multiple lines of reasoning. Maybe you can combine the reasoning at some point, or you may not want to. Like in this paper, you don't even need to combine the reasoning. You just have one line of reasoning, and then you do a separate evaluation for each line of reasoning, and you come up with, a final list of accepted reasonings. Yeah. So you could do something like that, and just by using LLMs as a pipeline to critique itself, to critique the critic, to improve on the errors by the critic. And that is enough to solve IMO problems. And that is really amazing because it's so elegant. It's so elegant. It's very, very human understandable. In fact, this paper has absolutely no math involved in the procedure. I mean, there's a lot of math involved in the problem and the solution, but in the procedure to generate the solution, there's absolutely very little math involved. In fact, I don't even have a math equation to include in this slide because it's just everything is in language. So we have reached a stage in life whereby the LM is able to take in arbitrary natural language instructions and be configured as part of a pipeline. And by just putting the pipeline correctly and just putting the right prompts at each part of the pipeline, you are able to get a good answer. One thing that they could improve is that, they did not use structured output generation. They actually use regex. So maybe this is not as robust. It might be better to use frameworks to get structured output. Yeah. I mean, maybe structured output helps to, makes the thoughts a bit more constrained. But in general, you still need some form of structured output. So I do think that's something that is lacking in their pipeline, but it works. So I'm not complaining too much. I like kudos to the two researchers. Let me just link their names again. Thanks for open sourcing your pipeline and sharing your information. It has helped a lot. Credits to Yichen Huang and Lin F. Yang. All right, thanks so much for sharing this. And yeah, I learned a lot from the paper that you have released and the code as well. With that, yeah, thanks so much for watching this and discussing with me today. And yeah, we'll see you again next week. Okay, bye.